Okay, so the next step is to add friction to these tidal waves, to the framework that we've established. So the momentum balance for a progressive wave will be what? Acceleration, pressure gradient, and friction. That's a general expression. But integrating vertically, so that's a vertically integrated momentum equation. So we have the accelerations, pressure gradient, and friction. But we have the stress at the bottom that we can be expressed like that in terms of the flow near the bottom. This C sub E is what? What did we say? Is that C sub E?
2.5 into 10 power minus 3.
Very good.
And no dimensions.
Excellent. It's in your heart right now, right? How did you do that?
I don't know. Stop there.
That's great. So if we can represent the near bottom flow as an oscillating flow, then we can represent this absolute value differently as a Taylor's expansion. So the bottom stress becomes in terms of the oscillating part like that, but then the absolute value of the cosine equals to that if we expand this absolute value of the cosine in a Fourier cosine series. To the lowest order, we get this factor 8 over 3 pi. So you can do it in the comfort of your home. You remember how to do the Fourier cosine series. That's where you get this 8 over 3 pi factor. So again, these here is equivalent to that. But you'd have to divide over h. Okay, so the sign, this is a bracket that got screwed up by the program in this computer. So again, we have the acceleration, pressure gradient, and bottom friction. But bottom friction, in terms of the amplitude of the tidal current, and then the flow here, the vertically integrated flow. And we have this 8 over 3 pi. So we can call this 8 over 3 pi times the drag coefficient times the amplitude of the tidal current over h. We can call that R, which we can call the linearized bottom drag coefficient. And what are the units of that R? What are the units? Right. Meters per second over, it's 1 over second in this representation, 1 over second. This is non-dimensional. This is meters per second over meter.
Oh, we're not taking into account the second U?
No, the U.
Oh, okay.
No. So just 1 over second. So these are the governing equations for a progressive tidal motion with friction. So there they are again, momentum and continuity. And using R equals that, as defined before. And if we define a mu, which is a friction factor, that depends on this R divided by twice square root of GH, then the solution for the amplitude of the oscillation is given by that. So it's the same as a plane wave, but it's modified by that exponential factor. What do you think that exponential factor does? It's an exponent to the minus x. So it indicates that the eta will decay exponentially because it's a minus x. It decays exponentially as we move into x, into the estuary. So frictional effects will take care of will attenuate the wave as it propagates in. And the same with the current. The current is similar to the expression before, but we have this eta to the minus mu x and this factor in the denominator. And also this phase lag between eta and u. This that phase lag is equal to the arctangent of the frictional linearized friction coefficient over twice the frequency of the wave. So what this tells us is that the maximum current precedes the maximum surface elevation. And there it is again. An animation from there. So this is a progressive wave that attenuates as it progresses into the estuary. I don't know if you see it on the screen there. There it is. You can see the amplitude decreasing from a value of 3 at the surface, at the mouth, to a value of, what is it, 0.5? Is it 0.5? Mm-hmm. So here's looking at it in an isomer. You can see how the amplitude decreases as the wave progresses. So that's a graphical representation, the graphic representation of this. Therefore, 8 hours for this. There's the other one. So that was a progressive wave. Now let's look at the effects of friction on a standing wave, on a standing tidal wave in this wave. So for resonance to appear, we need the flow to be 0 at the head. And what we have is that the surface elevation has two waves traveling in opposite direction, and the flow also two waves in opposite direction. And so that would be a standing wave. That's a, I don't know if you see it on the screen there. Standing wave, any wave that goes in. So again, that's a graphic representation of that. All those equations that are shown there. Plate standing wave attenuating again from an amplitude of almost 6 at the mouth to an amplitude of 1 at the end. There it is. This is what might be happening in Ponce de Leon Inlet. So my guess is when you go out to Ponce de Leon, you see something like this. The amplitude at the mouth is large, and then because of the system is quite shallow, there's a lot of friction, and then the amplitude might attenuate as you go further into the creeks that are upstream into the system. So you might have a behavior that might be represented by this except. Now, an exciting effect, the effect of rotation. I have to come back. The effect of rotation now. So now what we have, let's eliminate friction. We have the plane wave in the longitudinal direction. In the lateral direction, we have that momentum balance. And this momentum balance is what is this called? It's the same as the momentum balance across the estuary. Geostrophic, pressure gradient versus Coriolis. But notice that there's no density gradient here. It's the pressure gradient is provided by the slope of the surface across the system, across the channel. And that's the continuity equation. The solution to that is, again, something that looks very similar to the plane wave, but it has, what does this exponential tell you? What's happening to the wave in the y direction? Decays exponentially away from a waveguide, and over a distance r, where r, does anybody know what r is? is the Rossby radius, and the Rossby radius equals square root of GH over Coriolis. So here it is again. The distance over which this wave will propagate along a basin, decaying across its direction of propagation, and the distance over which it decays exponentially is given by that Rossby radius. Square root of GH over F, where F is the Coriolis parameter. So this is called a Kelvin wave. Some of you have taken physical oceanography, maybe you talked about this, but I don't know if you did. And these are very beautiful waves. You see that? So you have a plane wave propagating along the coast with the largest elevation where? Where's the largest elevation of this wave? Away from the coast or along the coast?
Along the coast.
Along the coast. Decays exponentially away. So you can see that the oscillations, where are the oscillations larger? Along the coast or away from the coast? Along the coast. You can see that. So that's a plain Kelvin wave with this type of solution. Now there's a Kelvin wave. Now it's showing the elevation and the flow associated. So it's showing both of these fields. Notice that the flow is strongest here or here. You don't see any arrows over here. Right? The flow is strongest here, decaying exponentially away. What would happen in the southern hemisphere though? This is for the northern hemisphere. In the southern hemisphere, you need a wall on this side, and the current and elevation would be stronger here than here. Notice that also the elevation, which is represented here by the shades, the elevation decays away from the boundary. So the most intense colors are along this boundary and decaying exponentially. So that's a plain Kelvin wave. So sometimes tides behave as Kelvin waves when they travel along the coast. Now, that was a progressive wave. If we look at the effect of rotation of standing wave, now we have two Kelvin waves of equal amplitude going in opposite directions. That's the so just so that it gets recorded, I'll do it here too. So we have the two waves traveling in opposite directions, and the flow will be given by the same expression. Notice that the elevation and flow are again related to C over A. So the valuable thing about this, and for any plane wave, is that with the amplitude and the depth, the amplitude of the wave and the depth of the water column, you can guesstimate, you can get an estimate, an approximate estimate of how strong the current will be. And this works very well in natural systems, a simple model like this. So say for a wave of amplitude, for a tidal wave of amplitude 1 meter, over 10 meters depth, what's C? C is the square root of 100, which would be around 10. So this would be, this C over H would be around 1. So the current would be around 1 meter per second. And that's not unusual to observe. So this is a useful relationship to use, even though it's quite simple, that you can estimate how strong the tidal currents in an estuary will be just by looking at the depth and the amplitude. So coming back to the standing tidal wave affected by rotation, there's no flow in the transverse direction. P equals 0. So that's the solution. And now instead of having lines of no motion, like in the standing wave, we have the point of no motion is the node of the wave. instead of having nodes, we are reduced to a central region, which is called the amphidromic region, where the elevation doesn't change or changes very little. So there's no motion at that amphidromic region. So the interference of two geostrophically controlled simple harmonic waves, which are these two, produces a change from a linear standing wave to a rotary wave. So we have now a rotary wave. See if you can see a rotary wave. This is a standing wave affected by rotation. Can you see a rotary wave? You might be able to see it in this other representation better. So both in the flow is the arrows, obviously, and the elevation is a different shade. So you can clearly see, I hope, but you can clearly see the amphidromic regions. Can you identify the amphidromic regions? Where are the amphidromic regions in this representation? Give me the x and y coordinates of the amphidromic points. 200 and 0 is 1, right? It's clearly, there's no flow there, and the elevation rotates around that point. And we have another one around 700 and
770. 750.
Yeah, I think, let's see, this is 750. Right, 750. So there's the other amphidromic point. Notice that the response will be different when we change the depth, because this depends on the flow depends on that. So the strength of the flow will depend. But the area won't depend. And depends on, well, it does depend on depth because of the exponential decay. Depth is here in the Rossby radius. What is this R, you said? Equal to what? If the R equal this R, the exponential
Something
equal
by
to
F over F. C over F.
something by that. You can't forget that other C. I mean that C. You can't forget it because it's part of your morning session. All right. So we'll come back to this.
Are these really the superposition of two complements going in opposite directions?
Yeah.
Because don't complements always have to go super close to the right?
Say again.
Don't complements always propagate with the close on the
Right.
right?
Yeah, so in this case you need two curves. This is a basin, this was a basin. You won't get a standing wave, a standing Kelvin wave in an open coast. You need a basin that is two coasts and a head. So this complex, right here.
I think so they're on opposite sides of the estuary?
Yes.
Okay.
So it comes. This diagram you can see the development of an amphidromic circulation. And you have an incident Kelvin wave here. Notice that elevation is higher here than here. And then this boundary is closed, this boundary is closed, and also this boundary is closed. So this is like a gulf. So as it gets to the head of the gulf, it just goes around like a Kelvin wave, again with the highest elevation here, decaying exponentially away from the coast, and then it goes around here with the highest elevation here, decaying exponentially away. So there's the amphidromic point where the elevation doesn't change. And so one way of seeing it is in this gulf, these are lines of equal phase, so the wave propagates in this direction, so counterclockwise, with the highest elevation on the right all the time. So this is a theoretical distribution for a simplified geometry. Now if you go to the Gulf of St. Lawrence, in the St. Lawrence River estuary, you have an amphidromic point here where the phase progresses like this, counterclockwise, and the maximum elevation is found along the coast. As shown by these the broken circles, those are the lines of the same elevation. So this 1 meter here, 2 meters, so more than 2 meters along the coast. As the amphidromic wave progresses counterclockwise. But in general, in the oceans, you also have amphidromic points. These are lines of equal phase. So you see a nice Kelvin wave here propagating toward the north. And you see a nice Kelvin wave here propagating toward the south in the southern hemisphere. So those are free Kelvin waves. And when the Kelvin wave is bounded in the Gulf, then you can have an amphidromic. You can have what you were asking, Kelvin waves traveling in opposite direction. So again, you can have amphidromic points in the tides in the ocean in general. Those are points where the tides are minimal. And examples of gulfs that exhibit amphidromic points. The Red Sea, on the left side, you have cotidal lines, that is, lines of equal phase, and the co-range lines on the right. So you have, whenever you have the cotidal lines going around a central point, or that is the cotidal lines converging toward the point, that's an amphidromic point. And you can see how it progresses from 0 to 2 hours to 3 to 4 to 5. So a counterclockwise progression here. And you also see it in the elevation. There's half a meter, 1/4 of a meter in this region, half a meter here. So you can see that the minimum tidal range is right here. It coincides with the convergence of phase lines to that point. So that's called an amphidromic point. Theoretically, you can obtain different amphidromic points as a function of friction. So this mu parameter is the same as we showed before. In this case, mu equals 0, meaning that there's no friction. So in these examples that I'm showing, this boundary is open and all of the other three are closed. So you have a nice amphidromic point in the middle of the basin. The co-phase lines converging to that point, and the co-range lines expanding, growing away from that. So that's 1/4 of a meter, half a meter, 3/4 of a meter, and 1 meter. Now, when friction starts to increase, the amphidromic point moves toward the left boundary. The left, as in the with respect to the wave that enters, that's toward the left. So that's the amphidromic point moving toward the left. And then as friction increases even more, then you have what's called a virtual amphidrome, or virtual amphidromic point. The amphidromic point is located on land now. It's not on the water, but on land. And you have the convergence of co-phase lines like that, and the co-range line showing a minimum there. And even with more friction, the amphidromic point becomes even less evident. But still, you can see it because of the cotidal lines converging toward that area, and that area showing a minimum in range. So if I show you these distributions of cotidal lines and co-range lines in the Chesapeake Bay, where would you find amphidromic points here? This is the phase, so the phase is propagating in that direction. Okay. And the amplitude is smallest here, increasing concentrically away from that, and then you have a local low also here. And I'm telling you that because you don't see the numbers, and I've already given you the answer, but can you see the amphidromic points? Where do you see the amphidromic points? One is clearly located here. So this is a virtual amphidrome, right? And this is for an estuary that we are more or less familiar. And the other one is not that obvious with the co-phase lines, but the co-phase lines are converging here, and that's a minimum in amplitude. So there's another virtual amphidrome, but this one is more dramatic. This doesn't mean that there are no tidal currents. It means that there are no M2 tidal currents, or very weak M2 tidal currents. Maybe you have diurnal tidal currents in that location. So these virtual amphidromes are for the harmonic for which you are drawing them. So in this case, it's the M2 only. Okay. For the diurnal, there are no amphidromes. The diurnal harmonic. So there are the amphidromes like that. So those were from observations. These are from numerical simulations. And you can see more or less consistently the virtual amplitude in this region and in that region here. All right, so I think no, we still have. So we'll now talk about how the wave gets rectified, gets modified. The tidal wave gets modified as it enters the estuary, and that can be understood from the fact that an oscillating flow can produce a mean current or a residual. How can that be? Let's think of wind waves. As wind waves approach the coast, they get modified, right? They get transformed. They get, as we call here, rectified. Although you don't use that language for wind waves, but let's say wind waves get rectified. They get modified. How do they get modified, and do they produce a mean flow? We know that they produce a longshore current. How do they produce longshore current? Okay, and so how does that produce a current? So say if you think the orbital velocities of a wave or a sinusoid wave, if you average over a period of a perfect sinusoid, what's the average of that? 0. So how do you get a non-zero? Because the wave gets modified. It gets steep, maybe, and the troughs are shallow. So when you average, you get a positive, a net displacement, net flow into the. So that's what's called, in fancy words, the stress. What's that called? Huh? Well, the Stokes drift, yes, but that also sets up the tensor. Stress what? It's the one that produces the mean currents. The waves produce mean currents through the stress tensor. Huh? I think that's what it is. I'm not sure if that's the right nomenclature, but the stress tensor. So that's again because the waves become distorted. The same thing, tidal waves will become distorted and they will produce a mean current. And that distortion or that rectification, we think it is from nonlinear interactions. And those nonlinear interactions in the case of tidal waves arise in sharp coastline bends or in bathymetric gradient. So this is a nonlinear phenomenon. And what happens is that energy is transferred from the dominant tidal frequencies to higher harmonics. That is, in the case of an M2 tide, you will generate through nonlinear processes, and we'll see this later toward the end of the course in more detail. You'll generate higher harmonics, that is M4 and M6 frequency. The M4 has a period of 6 hours approximately, so it's 4 cycles per day. And the M6 has a period of approximately 4 hours, or 6 cycles per day. But in addition to produce higher harmonics, just like wind waves do, you produce mean flows, so flows with 0 frequency. So there are 3 mechanisms responsible for transferring this energy from the dominant frequency to the mean flow. And you can study them from vorticity tendencies. You're going to read this paper later on. After you hand in the next homework, you're going to read this paper and another paper related to tides. But these are the 3 mechanisms by which, the 3 physical mechanisms that can be explained through vorticity tendency, by which the fundamental frequency is transferred to higher frequency and to a 0 frequency. From the fact that the conservation of potential vorticity, the flow moving from deep to shallow. Do we know potential vorticity? What is potential vorticity? Potential vorticity is relative vorticity plus planetary vorticity. You know what relative vorticity is? relative vorticity for a flow is a tendency for it to rotate. So you can imagine it as if u is the flow in the x direction, so the relative vorticity would be dv dx, the changes of the flow in the v direction with respect to x, minus du dy, the changes of u with respect to y. So that's a tendency for the flow to rotate. So dv dx, and we write it here on the board, the relative vorticity, we call it zeta, which equals dv dx minus du dy. That's relative vorticity. And then potential vorticity, which we call capital Phi, equals relative vorticity plus planetary vorticity divided by the depth of the water column. H. So zeta has units of what? Seconds. And F has units of 1/2. So we're adding apples and apples here. So we have 1/2 divided by, so the units of this potential vorticity is 1/2 over length of the meter. So what happens? Imagine that the flow is moving from deep to shallow. In the ocean, this quantity needs to be conserved. Needs to be conserved. So if the flow moves from deep to shallow, it means that, and if the relative vorticity doesn't change, so the numerator doesn't change. Sorry. Let me backtrack. Theta, this theta has to change. So F doesn't change, the Fourier parameter doesn't change. If H decreases, what needs to happen for the potential vorticity to be conserved? Theta has to increase. If H decreases, theta has to decrease. So the way it decreases is by acquiring negative vorticity, negative relative vorticity, which is a clockwise vorticity. So that's what we see here in this arrow, clockwise vorticity. The flow acquires a clockwise vorticity when it moves from deep to shallow. And similarly, when the flow moves from shallow to deep, H will increase. In order to conserve potential vorticity, theta has to increase. So we have to add relative vorticity to the fluid, positive vorticity, which is a counterclockwise vorticity. You can see how a counterclockwise rotation will be positive from this relationship, and how a clockwise vorticity will be negative. So anyway, by conservation of potential vorticity, you generate this rotation of the fluid that generates nonlinearities that will transfer the energy from the fundamental frequency to a zero frequency. Then you have the lateral variations of bottom stress. You have that where the velocity is stronger. As the flow goes around the point, it accelerates, and there's more bottom friction here. So this will tend to create a counterclockwise circulation, counterclockwise vorticity or positive vorticity. And this vorticity will again transfer energy from the fundamental frequency to the zero frequency. In the same way, over a sloping bottom, the depth distributed friction force will be greater here because the water is shallower. In other words, friction is more efficient over this shallow water than here. And again, that will tend to create, because of the distribution of these arrows, it will tend to favor a counterclockwise circulation. So that's because of the lateral shear and the depth distributed friction force. So because of these three mechanisms, you can have vorticity that transfers fundamental frequency variations to zero frequency variations. And that's how the tidal flow and the tidal elevation may become rectified. Again, and there are other mechanisms that we'll talk about later on in the course, but these three are from the point of view of potential vorticity tendency. And that's how the tide gets modified as it gets to shallow waters. So you're going to read a paper later on about this. So that I said, that the tidal flow oscillations at a single frequency will generate tidal vorticity by those three mechanisms. And because of nonlinear effects, that is the product of U times U, the vorticity generated will not only be at the fundamental tidal frequency, but also at higher harmonics. Okay, let me show that now. This is something that I should have shown you before. So we have U times U. This is the same as saying U amplitude of the sine, say equals to general times UA sine. So this is a current with a sinusoidal fluctuation. This is a time. So the product of U, which is a nonlinear effect, will give you UA squared, a sine squared T. And this is approximately, well actually let's do cosine because it's easier. Cosine squared. The cosine squared gives you, it's the same as UA squared of 1 plus 1/2 of cosine twice the frequency. Basically, the frequency here. Twice equal. So this cosine squared gives you a zero frequency term and a term with twice the frequency. That's how wind waves also produce mean flow in higher harmonics. Same mathematical explanation for wind waves and for tidal waves. So that's what said. That's what says there in words. Oh, I have it here. So there you have it. The cosine square equals 1/2 of 1 plus cosine of twice the frequency. And remember, I have it there. So there it is. The explanation of what it says here in words. So these three mechanisms that we saw schematically can be identified from the vorticity equation. We can derive the vorticity equation from the depth average two-dimensional momentum equation, which is appropriate to barotropic tidal motion in shallow area. So this is in vector notation, this is the 2D momentum equation. You have the advective terms, the local acceleration, the advective terms. This is what is it? Omega is the rate of rotation of the Earth. So this is the Coriolis term, pressure gradient, bottom friction, and horizontal friction. So we take the vorticity of this equation that is taking the curl, the V component differentiating it with respect to X, and the U component differentiating it with respect to Y, and then subtracting one from each other. You can do it again in the comfort of your home. And you'll get this vorticity equation. Now, this equation is in terms of theta, which is dV dx minus du dy. Notice that it looks similar to that up there. So what we have is that out of this term, the local changes of vorticity and the advective changes of vorticity, we have the total changes of vorticity. Then we have this term that is the potential vorticity conservation. Notice here we have relative vorticity plus planetary vorticity over depth of the water column. So that's the potential vorticity. As the potential vorticity conservation term. Then we have the lateral shear, the sloping bottom, and these two dissipate vorticity. So these are dissipative processes. So these three are the generating mechanisms that we saw schematically. The sloping bottom, the lateral shear, and the potential vorticity conservation. An example of this, of the generation of vorticity, comes from a study from 1990. The flow around this protrusion. What they did was repeated this trajectory several times during the several tidal cycles. And with that, they were able to separate the tidal from the non-tidal flow. This is in Massachusetts. Cape Cod, Woods Hole Oceanographic Institution is here. So it's right across this channel from Woods Hole in Martha's Vineyard Island. That's that. that headland. So you can see that during ebb, maximum ebb, you have the vorticity being generated on the lee of the head. Then this is at end of ebb, slack waters, you have these two gyres, counter-rotating gyres. During flood, you have the gyre, the vorticity generated on the other side of the head, and at the end of flood, you have this clockwise gyre, very well described. So this is an oscillating flow that's interacting with a headland that will generate a mid flow. You can see it's not symmetric about the headland. There's an asymmetry on both sides of the headland. So that's injecting energy from the fundamental frequency, which is the tidal frequency here, to a zero frequency, which is a mean flow, a pair of counter-rotating gyres. So that's one way of getting a zero frequency flow. That's how the tide gets distorted from a zero frequency flow. From a fundamental frequency flow to a zero frequency flow. So there's the distortion of the tide here in this shape. Okay, any questions? Okay.
Is that a flying point?
No, nothing to do with the amphidromic point, because these are tidal residual flows. We're not looking at how the tide behaves in the basin. We're not looking at so this would be how the tide behaves in the basin. So if you wanted to compare it to an amphidromic point, you'd have the amphidromic point here, then here, or here, then here, and here. So that changes quite a bit. So on the mean, there's no amphidromic point. Because the elevation, again, you have to look at the elevation too, not only at the current. These are currents. So the elevation here will be
So the
different.
amphidromic point has to be stationary throughout the whole tidal cycle?
Right, exactly. Any other questions? Okay, so remember that